And now we have vibratory motion. In this video, we take a look at the concept of periodic motion. Consider an object attached to a spring. So you have a spring fixed at one end, and you have an object attached to the spring, and you pull the object, stretching the spring, say a distance x or displacement x, from equilibrium position. Equilibrium position is our zero position, x is equal to 0, unstretched, uncompressed spring position. So you pull the object, resulting in the spring being stretched by distance x. As a result, the spring will apply force on the object, F spring, such that if you let go of the object, if you release the object, because of F spring, because of the action of the spring, the object will move back and forth repeatedly. This back and forth motion, this repeated motion, is referred to as vibratory motion. The simplest type of vibratory motion is referred to as periodic motion or simple harmonic motion. Periodic motion or simple harmonic motion is characterized by constant amplitude. A is constant. Amplitude refers to the maximum displacement from equilibrium position. So again, equilibrium position is x is equal to 0 position. The maximum displacement that the object can reach from equilibrium position, that's amplitude A. So on this side, A. On this side, A. A is constant for periodic motion or simple harmonic motion. Periodic motion is also characterized by constant period. Capital T, period, is constant for periodic motion or simple harmonic motion. Period is time for one complete vibration. One vibration or one cycle is the motion that is being repeated. For instance, say the object started at this position, it moves, and then goes back to the original position. That's one cycle or one vibration. And that vibration, that cycle, that motion is being repeated in the vibratory motion. So one vibration, one vibration, one vibration, and so on. If the object started at equilibrium position, one vibration, the object goes back to its original position. So one vibration, one vibration, one vibration, and so on. And the time for one vibration is the period, and the period is constant for periodic motion. So say the period for a particular vibratory motion is 10 seconds. So 10 seconds, 10 seconds, 10 seconds, 10 seconds. The period of the vibratory motion, the period of periodic motion or simple harmonic motion is constant. We use the spring to illustrate vibratory motion. That's because spring motion is an example of vibratory motion. In particular, spring motion is one example of periodic motion. And because the spring is the one responsible for maintaining the vibratory motion, spring force is referred to as the restoring force. The restoring force is the force that is the one that is maintaining the vibratory motion. And other types of periodic motion have different types of restoring force. For spring motion, the spring force is the restoring force. Thus, F spring is equal to negative kx, Hooke's law. Magnitude of F spring is just kx. We remove the minus sign, and the vectors x and F spring are now just magnitudes. Magnitude of F spring is equal to kx, where k is the spring constant, unit is Newton per meter. In addition to period, we have frequency. Frequency is the number of vibrations per unit time. Going back to the previous slide, if one vibration, starting from here at this location, the object moves, then goes back to the original position, that's one vibration. If period is the time for one vibration, frequency is the number of vibrations per unit time. For instance, if in 1 second you counted 1, 2, 3, 4, 5, 5 vibrations in 1 second, the frequency is 5 vibrations per second. And the unit for frequency is hertz. It has its own unit per second. It has its own unit, hertz, Hz, 1 hertz. So 5 vibrations per second, that's 5 hertz. Frequency and period are related to each other. They are inversely proportional to each other. Frequency is equal to 1 over period. They are inverse of each other. And since for periodic motion, period is constant, that means frequency is also constant. The motion of an object undergoing periodic motion is described by the following equations. We have the position function x, the velocity function v, and the acceleration function a. X is equal to a cosine of omega t plus phi, v, which is velocity, rate of change of position. So v is just dx over dt, differentiating the equation of x with respect to time, we get negative a omega sine of omega t plus phi. And acceleration is rate of change of velocity with respect to time. So differentiating the equation of velocity with respect to time, we get negative a omega squared cosine of omega t plus phi. Position function, velocity function, and acceleration function. Omega is referred to as the angular frequency. Unit is radians per second. It's basically frequency of the vibratory motion expressed in terms of angle radians, in radians. Omega is just equal to 2 pi divided by period. And since period is the inverse of frequency, angular frequency is also equal to 2 pi frequency. And since period and frequency are constant for periodic motion, the angular frequency for periodic motion is also constant. And phi is the phase constant of the vibratory motion, and it defines the position of the object at t is equal to 0. It defines the initial position of the object. And phi is in radians. So note, angular frequency is radians per second, whereas phase constant is in radians. So what that means is the quantity inside the trigonometric function is in radians. So when using this equation, be sure to set your calculators to radians because the angle inside the trigonometric function is in radians. The same goes for the velocity function and the acceleration function. Additionally, the maximum value for x is given by a, maximum value for v is given by a omega, and maximum value of the acceleration is given by a omega squared. These values for the maximum value of x, maximum value of v, and maximum value of a are the amplitudes or magnitudes of the position function, velocity function, and acceleration function. X, the amplitude is A, V, the amplitude is A omega, and A, the amplitude is A omega squared. Maximum value of X, maximum value of V, and maximum value of A. Also, the angular frequency is given by square root of k over m, where m is mass of the object undergoing periodic motion, and the total of the mechanical energy, kinetic energy plus elastic potential energy, or simply potential energy if you will, the maximum, the value rather of the mechanical energy at any location in the vibratory motion is given by 1/2 Ka squared. So again, the total mechanical energy at any location in the vibratory motion is 1/2 Ka squared. So for instance, if you have an object undergoing spring motion, again, spring motion is periodic motion. So the object is moving back and forth at any location in the vibratory motion. The total mechanical energy is 1/2 Ka squared. So if you look here, 1/2 Ka squared. If you look at the equilibrium position, the total mechanical energy is 1/2 Ka squared. If you look at this location, at this position, the total energy is 1/2 Ka squared and so on. Note that omega is equal to square root of k over m and total mechanical energy is equal to 1/2 Ka squared. Both of these equations make use of k, the spring constant. That tells you that these two equations are applicable only to spring motion. It's because they make use of the spring constant in the equations. And that's it for now. That's it for our discussion on periodic motion. In the next video, we'll continue our discussion on vibratory motion. In the next video, we'll take a look at a few examples. So once again, that's it for now. Thank you for watching.